making that connection between velocity and how fast your position changes can help us start to really understand this idea of derivative and what it can mean for us as we apply derivative, this idea of a derivative, in real world problems. So if the rate at which your distance changes is velocity, and velocity is the derivative of distance or position, then let's think about, like, what's the next step? What's the rate at which your velocity changes? Well, we call that acceleration. And that turns out to be exactly the derivative. The derivative of velocity is acceleration. So, acceleration is the derivative of velocity. But velocity was the derivative of position. So that means acceleration is the second derivative of position. So you can use either one of these notations. You'll use both of them multiple times all year long. So you can see what the notation I have here, and that goes on your nose paper. So here's an example just to get us warmed up. If the position of a particle is given by s of t is t squared plus 4t plus 4, can you find a formula, an expression for the acceleration of the particle? So yes, because we know position, which means we can find velocity, and if we can find velocity, we can take its derivative to get acceleration. I'll move me out of the way. So we'll need the second derivative. So first I'm going to start by finding v of t. There's no way to jump right from the s function, the position function, to acceleration. You're going to have to go through that middle step. So I'm going to take the derivative of position to find velocity. That's this 2t plus 4. The derivative of t squared is 2t. The derivative of 4t is 4. Now I'm going to find the acceleration by taking the derivative of the velocity. Well, the derivative of 2t plus 4 is just 2. So that is my acceleration function. It happens to be constant. The acceleration at any time is 2. So when it's time to figure out the acceleration at time t equals 4, I'm going to replace the t with 4, but it doesn't matter. My output is constant. It's always 2. So the acceleration at time 4 is 2. So we'll spend a lot more time on this in chapter 4, but just to sort of lay the groundwork, let's understand the relationship between the graph of the distance function and what we can figure out about velocity and acceleration. So I'm going to start by focusing on the velocity. What I have here is a function. This is the graph of distance versus time. We know the derivative of the distance function is velocity, and we know derivative means slope. So I'm going to write slope of, let's call this the s function, s of t. Slope of s equals velocity. The slope of s would be s prime of t, but we know s prime of t is velocity. So just notice here, this first arrow, this says velocity is positive and increasing. Let's focus here on the positive. The velocity is positive because the slope is positive. At this point on the graph is moving, this position function is increasing. So going uphill, that means the slope must be positive. So here, my slope continues to be positive. My function is still going uphill. And that's why I have positive velocity all the way to this point. At this one place where my function seems to be taking a turn, you can imagine drawing in the tangent line. If you tried to draw in the line that sort of just touched your curve in one place, you could see here the tangent line would be horizontal. That means the slope is 0. That means the derivative is 0. That means the derivative of position is 0, which means velocity is 0. Here, now that my function is sort of turned around, my position function starts going downhill. It starts to decrease, which is why I have negative velocity, because velocity is the slope of the position function. The function's going downhill, so slope must be negative. So let's back this up a little bit and understand sort of this next idea. So we've understood a little bit about why velocity was positive or negative or 0 in each of these little places. So what is it that makes me know that the velocity here is increasing? Well, velocity is the slope of this function. So the slope, you could imagine sort of drawing in little line segments to cover this up. They're kind of flat, they're kind of flat, they're kind of flat, but then they get steeper and steeper. That means the slope is increasing. So slope is becoming steeper, that means the slope is increasing. And since slope is velocity, velocity is increasing. Here, if you try to draw in a line segment in that section of the graph, it kind of looks linear. That's why we say velocity is positive, because we're going uphill, so the slope is positive, but it's kind of constant. This seems linear in this little section. That's where this constant comes from. Now here, after a little while, the position function is still going uphill, so it's still increasing, but now it's sort of flattening out. So even though the slope is positive, it's not as big anymore. So that's why I say the velocity is decreasing here. So we continue decreasing, decreasing. So it was kind of flat, and now it's going negative. So a little bit positive to negative, that's a change that we're decreasing. Here, again, that seems linear in that section. That's why the velocity is constant. And here, this was going downhill, like pretty fast downhill, and then it sort of flattens out. That tells me that I'm changing from something that is negative and kind of very negative to closer to zero. That's an increase. That's why my velocity is increasing down here in this last section. And then let's talk about acceleration. Acceleration is the derivative of velocity. The same way that we could tell a little bit about, it was the slope of the position curve that told us whether velocity was positive or negative. So if the position curve was increasing, that meant positive slope, so positive velocity. When the position curve was decreasing, going downhill, that meant negative slope, negative velocity. So now what we want to do is to think about what velocity was doing and relate that so relate how velocity was changing to acceleration. Since acceleration is the rate of change of velocity, it tells us how velocity is changing. So here, whenever velocity was increasing, acceleration must be positive, because acceleration is the slope of velocity. If velocity was increasing, that meant it was going uphill, which means its slope must be positive. Anywhere velocity was constant, well, what's the slope of a constant? 0. So the derivative of a constant is 0. Anywhere velocity was 0, its derivative, no, anywhere velocity was constant, its derivative, acceleration, must be 0. Here we said velocity was decreasing. That means velocity was going downhill. Notice this is not a picture of velocity. I had to make that picture in my head. And so I know acceleration is negative here. Whenever velocity was constant again, I had a 0 acceleration, because the derivative of a constant is 0. And here, where velocity was increasing, that tells me that acceleration was positive. So we'll have lots more chances to talk about how to look at a graph and sort of feel that, get a feel for the first derivative and the second derivative just by looking. But just lay the groundwork. This is your first time. It's important to introduce it early so you can have a lot of time to sit with it until we get to chapter 4 when we'll really dig in. Okay, so here's the cool thing. If we have a function, f of x, that describes some quantity that changes, we don't have to worry about just dealing with position and velocity and acceleration. We can talk about the rate of change of other kinds of things, the rate of change of potato consumption in the United States, or the rate of change of your GPA over your senior year. And so just make that connection. You could find the average of that change over time using f of b minus f of a over b minus a. But if we want to know how fast something is changing right now, we let those 2 points, a and b, get closer and closer together. That's instantaneous rate of change. I know you've seen that expression in your notes. It means the same thing as derivative. Instantaneous rate of change right now. What is my slope at this exact point? What is the slope of the tangent line? They all mean the same thing. They all mean derivative. So that means we can find the rate of change of other kinds of functions. So we know, for example, that the area of a circle is given by the formula A equals pi times r squared. You could now start to talk about what it means for the area of that tree trunk to change. How fast is it changing? So if I want to find the rate of change of the area of the tree trunk, I'm going to take the derivative of A with respect to r. So I have my little 2 is the exponent on the r that comes down to multiply. We have a constant multiplier. In this case, it's pi. It's still a constant multiplier. So the 2 times the pi times r to its new exponent is 1 less than the old exponent. And we get the rate of change of the area of the tree trunk with respect to the radius is 2 times pi times r. If I want to know how fast the area of the tree trunk, like cross-section, is changing at a particular moment in time, I forget what particular moment I asked you for. Okay, so what is the rate of change of that area when the radius is 4 feet? So notice a new notation. If I had called that, if I had called that function a prime of r and said that was 2 pi r, that's another good notation. Equally good. Then right now I'd be trying to find a prime of 4 by replacing the r with 4. So 2 times pi times 4 is 8 pi. Notice I've used this different derivative notation, which you need to have just as much experience with. But we don't treat it like function notation the same way you use these parentheses and you put a little input value in the parentheses. So this is the notation we use for this problem. If I've called my derivative dA dr, and I want to evaluate it at the time when r equals 4, I make a very tall vertical line, and I put a little tiny r equals 4 underneath it. So I'm going to highly recommend that you practice this notation. It takes some getting used to. So the rate of change of the area of the tree trunk with respect to the radius when the radius equals 4 is 2 times pi times 4, this same formula, but with 4 in the place of r, and that does equal 8 pi.